So this is a lecture about the continuation of the electric field. So we missed class due to a snowstorm, so I thought I could do the lecture as a video lecture. So we'll talk about electric field. So there is electrostatic and a gravitational force. And the electric field acts at a distance, so there's no direct push or pull, right? So it comes out of like we saw the electric force first, right? In terms of addressing concepts, but the electric field is something that comes just from the source itself. Usually people are uncomfortable a little bit with the electric field because it's very much like the gravitational field where it's there, but unless you have a mass that you put into the gravitational field, it doesn't feel a force. It's just the gravitational force exists. The gravitational, field exists. It's just like an electric field. So if there are charges, then an electric field exists. Those charges create the electric field. But you wouldn't know it was there unless you put a test charge in the field, and then you could see how the test charge moves, and that would tell you something about the field. So the electric field was conceived by Michael Faraday, and the electric field extends out from every charged object. And other charges, like I said, can interact with the field. And the direction of the field is determined by a motion induced on a positive test charge. And so I'll show an example of that in a minute. Here are a few examples of field. So we can have a temperature field where if we look at this map, every point on the map has an associated temperature or average temperature. And we can think about field as like a gravitational field. So we can see that the Earth has a gravitational field that's stronger closer to the Earth and is weaker farther from the Earth. And notice the direction, the field points towards the Earth. And then in the bottom figure, we can see that, that there's a gravitational field that's a constant for both of these masses. But the force due to that field is bigger for the mass 2 than for mass 1. But the field itself is exactly the same. So the gravitational field is given by the acceleration of gravity. And it, like I said, it varies with distance from the Earth, and it's different from the force. So here's an example of electric fields from a positive charge and a negative charge. And these arrows show the magnitude and the direction of the field. So those arrows are representing the field. But it also shows the magnitude and direction of the force. If I were to put a positive test charge into the field, like say farther away, out say here, what would happen would be if I put a positive test charge here, the charge here is going to feel a force and move this way. So this shows the magnitude and direction of the force felt by a positive test charge due to the source charge. And so if we have a negative charge creates a field that points towards the charge. And so if I put a positive test charge, say here, it's going to feel a force, and it's going to then move this way. This just talks about the magnitude of the test charge Q0. So a couple things to remember is that a test charge is a conceptual tool to help understand the magnitude and direction of the electric field. And the magnitude of the test charge is really small, and so it doesn't affect the existing charge distribution. So you can see here I have this test charge, and I have charges in my spherical shell, but this test charge doesn't cause the negative charges to move toward it. They're distributed evenly in this field, in the sphere. Whereas if you look at this one, this test charge is a bigger charge and has a larger magnitude, and so it's changed the distribution of the charge. So this would be the example we're talking about, a very, very small test charge with very small magnitude, so it's not going to have any impact here on this charge distribution. So a question that you'd normally do in class, but we'll do here. So a proton is released in a uniform electric field, and it experiences an electric force toward the south. What is the direction of the electric field? So if our proton, it's a positive charge, and it experiences an electric force towards the south, then the direction of the electric field is also towards the south. So you can see that. So remember, my positive charge is going to follow the field lines, whereas a negative charge would go against the field lines. So that's just another thing to remember. So here, this is the example. An electron, right, is a negative charge, and it's released in a uniform electric field, and it experiences an electric force towards the west. So what is the direction of the electric field? So here, if I had a negative charge and my electric field points towards the west, so it's pointing this way, then my electron's going to feel a force towards the east, so it's going to be opposite. So remember, an electron is a negative charge and it goes against the field lines. So if we wanted to calculate the electric field, we know that the electric field is just the force divided by the charge. And so we know the equation for the force is kqq over r squared. So if we're just dividing by q here, we get kq over r squared. And so remember, K is a constant. It's 9 times 10 to the 9th Newton meters squared per coulomb squared. Q is in coulombs, and my R is in meters. And so just looking here, what is R? Well, R is the magnitude of the vector going from my source charge to my point of interest. And so when I calculate R squared, I'm calculating it from the source, from the charge to my point of interest. And so when I calculate the field, if I'm looking for the field at point P, I put the tail of the arrow at P, and then I draw the arrow away from the test charge. So just here again, I have kq over r squared, right, and in the r hat direction. So the r hat direction is just away from the charge, radially outward. That's what the r hat direction means. And r hat just means that it tells you the direction that the vector points, and it has a magnitude of 1. So the electric field obeys the superposition principle. So if I have, for this example here, or for this example, I just have one charge, right? And so if I'm looking at this point, I'm going to have a field that points away. If I have a charge over here and I'm looking here, I'm going to have a field that points away. And then if I have two charges, I'm gonna find the field due to this one, which is going to point away, and the field due to this one, which is going to be up. And then the combination of the two gives me the net electric field. So the same thing here. If I want to find the field at point P1, I'm going to have to first find the field due to the negative 3q, so that's going to point towards it. The field due to this charge, which is positive q, so that's going to point away. So I'm going to have, so far I've got a vector this way and a vector this way. And then finally for the bottom charge, I'm going to have a vector that points this way. So I would have to take those together. They're all vectors, so I'm going to have to find the x and y components for each one and then add them up, and I'll get a vector, and it will have x and y components. So this asks, what are the magnitude and direction of the electric force on an electron in a uniform electric field of strength 2,000 newtons per coulomb that points due east? So right off the bat, remember that if my electric field points east and I have an electron that's a negative charge, then I know it's not going to follow the field line, so it's going to go west. So right off the bat, I can choose either 2 or 4, and then I know the way I'm going to calculate my the force is I'm just going to take my electric field times my charge, which is 1.6. So that's just looking at 2 times 16 is 32. So I know I'm going to have 2 as my answer. So a lot of people they will say, well, an electron has a negative charge, it's a negative charge, and they'll put a negative in there, and then they'll do the multiplication. I always say just use the magnitudes to find the magnitude of your force, and then in order to find the direction, look at the field lines and look at your charge and see if it's positive or negative, and that'll tell you your direction. Don't use your numbers or what you plug into your variables. Don't use negatives there. Determine your direction from the actual concepts in the physics. So an electric dipole is a combination of two charges. We can see here that water is a dipole, as an example of a dipole. And I can see if I represent this dipole as a negative charge and a positive charge together. So what happens with water acting as a dipole, when I take that dipole and I put it in my electric field, my field points this way. So I can think about this, that the field is showing me that negative charges would be here and positive charges would be here. And so it would make sense then if negative charges are here, then it's going to turn my dipole so that my positive charge is attracted to the negative charges here, and my negative side of the dipole is going to be attracted to the positive charges here. And so this dipole is induced or stretched due to the field acting on it because of the positive and negative charges. And so here, if I think about this dipole, right, and I want to usually the way when you have a dipole, you're either looking for the field on this axis, the y-axis, or on the x-axis. And so looking here, the electric field due to the positive charge is bigger than the electric field due to the negative charge. The positive charge and the negative charge have the same magnitude, but the positive charge is closer to my point of interest here. So since it's closer, it's a smaller number, and that's in the denominator, so this arrow is going to be bigger than this arrow. So my net electric field due to my dipole is up here. Whereas here, if I want to find what is the field due to my dipole, they're both equidistant from my point of interest, so the magnitudes will be the same. This electric field is going to, for the positive charge, is going to point away. This electric field due to the negative charge is going to point towards the charge. So the x components cancel, and I'm left with a down electric field. So here is an equation for when you're calculating the electric dipole. The dipole moment is given by the letter or variable p, and p is equal to q times s, where s is the distance between the charges. Notice that p is a vector, so the vector, the way I determine the direction of the vector p is that p points from the negative charge to the positive charge. So if I want to find the electric field due to my dipole, I can be on axis. So here would be on axis, and just like our last example, I was looking at a point up here, and to calculate it I would use this equation. And for the bisecting plane, I would be like looking over here like in the last slide, and I would use this equation. And the thing to note about this equation is I think this is the first time we're introducing 1 over 4 pi epsilon naught. So this whole fraction right here is actually equal to k. So this, you could also write this as minus k 2 times p over r cubed. So we've used p, our dipole moment, and remember that p equals q times s. So s is a length, and I have one charge. So that makes sense because I know E is equal to kq over r squared. So if I have, in terms of units, I have qs on the numerator, and then r cubed in the denominator. I have a length, cancels one of the lengths here, and I get my my formula back. But also notice that for a dipole, that the electric field due to a dipole is smaller than the electric field due to a charge because I have this r cubed here. So the r cubed makes my electric field smaller. And notice also that I have a larger electric field on axis versus on the bisecting plane, because here I have 2p and I only have 1p here. And so we'll work on the problems in the next video.